All right, so last time we talked about transition elements and coordination complexes, at least an introduction, some of the definitions that go along with that field of chemistry. So we talked about what coordination spheres were. They contain the metal and the ligands. Uh, this came about through a Lewis acid-base interaction where the ligand, that atom or molecule, had to have an atom within it with lone pairs of electrons that could donate those electrons into empty d orbitals centered on the metal. And then those electrons are shared by both the metal and the nonmetal, and that's a type of covalent bond. What makes it a coordinate covalent bond is that the origin of the electrons that are being shared originate from the ligand. Whereas, the regular covalent bond that you learned about in 200 came about from electrons centering on each atom, and then they come together and share those electrons in a molecular orbital. And we mentioned that when these metals have these coordinate covalent bonds, it changes the physical and chemical properties. So it changes their colors and also how they behave in chemistry. So we looked at that. We looked at some of the geometries that are associated with these complexes, and the little review from Chem 200. So when we have 6 ligands like we have in this picture with cobalt and ammonia, where ammonia is the ligand and there's 6 of them, the geometry is octahedral. We then looked at what affects the number of ligands, and many things affect the number of ligands. We just picked out 2 things and looked at how that might change how many ligands can form these coordinate covalent bonds with metals. And those 2 things were size and the charge transferred in that bond that was then shared. All right. Then we took a look at a couple more structures, square planar, which tended to come about with metals that have a D8 electron configuration. And then metals that have other electron configurations tend to form tetrahedrals if there's 4 ligands. We introduced the idea of monodentate versus polydentate ligands. The first polydentate ligand we looked at was ethylamine diamine, where the lone pair of electrons that centered on the nitrogens were donated into forming coordinate covalent bonds with cobalt. And so a structure looks like that. It's octahedral. It has a coordination number of 6, even though it only has 3 ligands. And the reason why is because ethylene diamine is a bidentate ligand. We looked at some other ligands that have more than one coordinate covalent bond, or more than one pair of electrons that are donated into empty d orbitals. We took a look at the chelate effect, which says when we look at monodentate ligands versus polydentate ligands, the polydentate ligands bind stronger to the metal, as evidenced by the higher equilibrium constants. That was the chelate effect. And so these are often referred to as chelating agents, these polydentate ligands, and they can be used in manufacturing of foodstuffs and also medicine. One of those ones you might find in your food is EDTA. This is a hexadentate ligand. Its formula is down here. It makes 4 oxygen coordination covalent bonds and the 2 nitrogens, and that makes up the 6 for an octahedral complex. We looked at how this special type of metal ligand interaction takes place in the porphine ring, which is important in plants and animals. Uh, when iron binds in the porphine ring, uh, we call it a heme group. When magnesium in plants bind to that porphine ring, it's chlorophyll. So we looked at some of the details of the structure of uh, muscle tissue and plants, chlorophyll. Then we went on to nomenclature, which is just a bunch of rules like we had before, and we had to apply these rules, name the cation before the anion, and so forth. Um, and we took a look at that and ended last time with an activity where you were to get some practice with nomenclature. And that leads us to the new material today. So any questions on anything before we hit the new material? All right. Okay, so we're going to look at isomers involving these coordinate covalent compounds. And isomers, not to be confused with isotopes, which you're studying now for the exam in nuclear chemistry. Isotopes differ in the number of neutrons from one element to the other, and they're the same type of element. Whereas isomers have the same molecular formula, but are different. Well, because of two reasons here for these complexes that we're looking at. So the category A, yeah, go ahead. Does someone have a question or a comment? No? Okay. So isomers have the same formula, but they're different compounds because they have different properties. Two subcategories are the structural isomers. Here we have A, here, and the category B, stereoisomers. Okay. Now, I think you'll find it easier to understand the structural isomers than the stereoisomers, but the stereoisomers are interesting in their own right and have lots of applications. And if you take the organic chemistry class, then you're going to get way deep into organic stereoisomers. So that's something that'll be important for organic. But anyway, here we have on the left the structural isomers, right? And there's two types of structural isomers. And when we take a look at them, you'll see, oh yeah, I understand why they call it coordination sphere isomers and two linkage isomers. Under stereoisomers, we have two specific categories. One, the geometrical cis-trans isomer, and the optical isomer. So with optical isomers, the reason why they call them optical isomers is because when you have these isomers, it's hard to tell the difference between them. And one way to tell the difference is the way they interact with light. And that's why they call them optical isomers. All right. There we go.
Professor, would stereoisomers be like the same as like resonant structures, like when we draw like the Lewis structures, but then you could draw it multiple ways? Is that like what a stereoisomer is?
No, not really. That's something kind of related, but different.
Okay.
A resonance structure shows two possible electronic structures, and each one of them are equally probable. So what is the true structure of that molecule? We can't say for sure because we can't see. So what we believe the true structure is some sort of a mixture between the resonance structure. And we can rationalize that by flipping bonds back and forth. And if I could write that out here, like for benzene, I don't remember, if you remember benzene, it looks something like that, where we have carbon atoms at each one of the corners, and then a carbon double bond carbon. So that means there's hydrogens here for each one. And so the resonance structure for this, I'm just going to draw the benzene ring without the carbon and hydrogen designations for this. So an equivalent structure for this would be where we flip those double bonds around that ring. And so they're equivalent Lewis structures for either one. So what's the true answer? We say that the true answer is somewhere in the middle of those two. And that's what we call resonance structure. And we have experimental evidence that that's true, because when we do experiments on benzene, like shine light on it and get vibration frequencies of the atoms and stuff like that, we find that these bonds in benzene are not double or single bonds, each one. They're an average between the double and the single bond. So if the single bond was 1.4 angstroms and the double bond was 1.2 angstroms, we find that each one of these bonds in benzene is 1.3 angstroms. And so the resonance, this idea of resonance works well for us because we can use Lewis models to represent what we find in the experiments. So that's different from stereoisomers, as you're going to see.
Okay, thank you.
Yeah, so that's just a little review on resonance structures, but you'll see when we get to stereoisomers that it's a bit different. Okay. All right, so we're going to take a look at the first one, the coordination sphere isomer. And this is very easy to see. So we know what a coordination sphere is. That's the sphere that encompasses the metal and the ligands. Okay, so here I have some general formula down here involving chromium, 3 chlorides, and 6 waters. But we know that when we form these crystals, we can get different formations of the coordinate covalent bond. For example, this first complex ion has 6 waters coordinated to the chromium in an octahedral complex. And then outside of that, in the salt, there's 3 chlorides. An isomer of this, a coordination sphere isomer, is the next one, where we take one of the waters and replace it with a chloride that makes a coordinate covalent bond. And then outside of this coordination sphere, we have 2 chlorides and a water, and so forth. And you can imagine as we go, there'll be more possibilities. So any questions on the coordination sphere isomer? I think that's probably the easiest one to see. The next one is pretty easy too, the linkage isomer. Now to see linkage isomerization, you really have to have a ligand that has 2 possible linkages. And here the ligand that has two possible linkages in this example is NO2. So NO2 can donate a lone pair of electrons from one of the oxygens and form this isomer with cobalt and the rest of the ammonias, or the NO2 can link up using the lone pair that's centered on the nitrogen atom to form the coordinate covalent bond and result in this isomer. Other ligands which have this ability are, for example, thiocyanate, where the sulfur has a lone pair of electrons that can donate, and the nitrogen also has a lone pair. So that can give rise to linkage isomerism. So that's the two examples under the category of structural isomers. They have different bonds. Okay, so with the linkage or with the coordination sphere isomer, for example, this first isomer has 6 coordinate covalent bonds from water. In this example, I only have 5 coordinate covalent bonds from water and 1 coordinate covalent bond from the chlorine, but the whole salt has the same formula. Okay. And lastly, this linkage isomer has, as we saw, different parts of that ligand that can lead to the coordinate covalent bond. In one case, oxygen, in the other case, the nitrogen. All right, now we move to the second category, the stereoisomers. And the first one that we're going to look at is the geometrical isomer in this category. And mainly this centers around what's called cis-trans isomerization. So I have 2 isomers here diagonal to each other in an octahedral complex. Right, so these are the 2 isomers. One is in the cis category, the other one is in the trans category. And same thing with these 2 guys down here. This one is in the trans category, and this one is in the cis category. This is called cisplatinum at the top. Now, cisplatinum, you can see the platinum in either one of these cases has 2 coordinate covalent bonds with chloride and 2 coordinate covalent bonds with ammonia. So the structure and the bonding is exactly the same, but because these ligands are in different environments, they lead to different structures and different molecules with different chemical and physical properties. For example, this one is violet, and this guy down here, I can't see what color it is because it's getting blocked, but it's a different color. Shoot. Anyway, it's whatever it says there, the color. And they also have different physical properties. So imagine you're looking at, say, the dipole moment on these guys. You're going to have a center of negative charge over the chlorines, and the center of negative charge is going to be right between them. And over here, the center of positive charge is going to be over here. So you're going to have a dipole moment, whereas in this structure down here, the trans structure, the center of negative charge is going to be right over the platinum, and the center of positive charge is going to be right over the platinum. So they cancel out, and this one's not going to have a dipole moment, so it's not going to interact with magnetic fields and things like that, whereas this guy does. Another property of cisplatinum is that it can be used in medicine for cancer. They've used this drug. It was one of the first drugs I think ever used to fight cancer, where this isomer is not used. All right. Any questions on the geometrical isomers of cis trans? Okay, now we get to finally the optical isomer. Now remember, optical isomers are called optical isomers because uh, the way they're distinguished is through their interaction with light. They interact with light differently, and we're going to take a look at specifically what that means in a second. But one illustration of these optical isomers, and sometimes they're explained this way, is that if you put your left hand up in front of a mirror, so say this is your left hand, then if you look in the mirror, it generates a picture of your right hand. Okay. So one way to see if you're dealing with an optical isomer is to do this test and see if that image that's generated in the mirror is non-superimposable, which means that it's different. Because if it's superimposable, that means all the atoms outside the mirror and in the mirror line up with each other, then it's the same molecule. For example, if I had, I don't know, if I had the water molecule over here, right, and I wanted to see what it looked like in the mirror, then it would look like this, right? And that's the same molecule. I can pluck this out of the mirror, I could build it, and then I can superimpose it on the original and show that it's exactly the same. Whereas if you did this for your left and your right hand, they're not superimposable. They're two different things. You can't, can you imagine walking around with two left hands? That would be pretty noticeable, right? So they are two different things sometimes, and when they are, that's when you're dealing with these optical isomers or non-superimposable mirror images. Like in this case, if I took this molecule or this coordinate covalent complex, it could be ammonia or whatever. It's a, oh, it looks like ethylene diamine. That's what it is, right? Because ethylene diamine has two connections from the nitrogen in that molecule. And this ribbon back here, there's a couple carbons in it. Couple carbons here, here, here. Now, if I build this, say with my molecular modeling kits that you may have played around with in Chem 200 when you were doing valence shell electron pair repulsion theory, you can build this, put it up to a mirror, and then build this reflection. Now, if I take that build from the reflection and I try to superimpose it on this, things won't match up. If I move it over, this ribbon over here at the top just isn't here. And if I rotate it, I can't match it up at all because they are two distinct and different isomers. All right. So most of the physical and chemical properties of these isomers, also known as enantiomers, and you'll get into this in organic, they'll ask you to draw out the enantiomers of certain hydrocarbons. So you'll have to get used to using that name as well. Optical isomers, enantiomers. What else do they call them? Oh, chiral molecules. If a molecule has a chiral center, then that's another way of saying if you put it up in front of a mirror, it's non-superimposable. So you're going to run into all these other names meaning the same thing. And so remember, we call these optical isomers because of the way they interact with light. Now, what's different about it? Well, the enantiomers or the different isomers rotate plane polarized light differently. And it tells you here just, what happens when you put in the different samples in the plane polarized light. But here's a picture that explains it. So the words are on the previous plate. I think the picture helps a lot better. Say we take some light source, okay, and we shoot it through a polarizer. So this light source has amplitudes, oops, in all directions. So it has amplitudes that come out of the page like that. So we have amplitudes of light. It's not polarized. It goes through a polarizer, and out comes the light that has amplitude in just one direction. Now we have polarized light, which goes through our sample cell. So here we have one of our optical isomers. And if we're checking out what happens to that plane polarized light, we might notice, as in this case, that it rotates to the right by a certain number of degrees from the zero axis. So it rotated to the right a certain number of degrees. And we call this isomer dextrorotatory, because if we have the other isomer in here, we change the cells, we put in the other isomer, that isomer is going to rotate the plane polarized light the same amount in degrees, but in the left direction. So we call that levorotatory, or the L isomer. So I think this is a pretty good illustration of why we call them optical isomers, because of the way we can detect the different ones. And we should note that because they are very similar in molecular makeup, a lot of the physical and chemistry properties are the same, but some oftentimes are found to be drastically different. For example, this thalidomide, it has two isomers, the S and the R form. It's another way to designate isomers. I know we just looked at the D and the L form, but it doesn't matter. One isomer of thalidomide was used in the late 1950s for women who experienced morning sickness. So it helped alleviate this morning sickness. But they had to stop that right away because babies were born with horrible birth defects. They didn't have, some didn't have limbs and so forth. And they stopped that in 1961, I think. And they found the reason is because this one form of thalidomide, the S form, kind of attacked any cells that were rapidly growing. And so you could see that that was not a good thing to give to a pregnant woman. Nowadays, I think they've started to do more research on this, and they've used this this isomer to combat things like cancers and tumors. That when they put it in a tumor, it restricts that tumor from growing. It can't spread out its blood vessels and things as good. And so they are finding some applications for this isomer. Now this leads to what's called racemic mixtures. So someone might say, well, geez, why don't they just use the other isomer to combat morning sickness, the one that doesn't cause those horrible birth defects? Well, that if I have two different forms of this isomer, the L and the D form, or the R and the S form, nature is going to want to take high concentration and spread it out. And what happens is, even if you took one of these isomers and found it in its pure form, uh, equilibrium is when we have a 50-50 mix of these. So it's going to, what they call racemate. It's going to convert to the other isomer until it reaches equilibrium at a 50-50 mix. And these are called, right down here, racemic mixtures. Now, the thing about racemic mixtures is when you put them in the plain polarized light, you have 50% rotating one way, 50% rotating the opposite. So the light passes right through, and it looks like you don't have any isomers in there at all. So that was another problem that they had to worry about when they were trying to detect the different optical isomers, when they ran into these things called racemic mixtures. Okay. All right. Now, this is kind of the last important bit in this chapter, where we take a look at a electronic structure theory called crystal field theory, and apply that in understanding, or better understanding, the color and the magnetic properties of these coordinate covalent compounds. So we start off by taking a look at color and what that is and how we perceive what we do and things like that. But anyway, what we're trying to do is better understand why, for example, a complex of copper that has 6 water ligands is a different color than that copper complex with ammonia. We know that it must have something to do with the partially filled d orbitals and electronic transitions, because we saw that in atomic transitions, you know, how light was absorbed and then light was given off. So we're going to just take a quick look at what light is again. So here we have the electromagnetic spectrum from high energy to low energy, high energy blue at this end to low energy red at the other end, and all the other frequencies in between. We have ultraviolet to the high end of our visible and infrared to the low. Another interesting way to look at it, though, is with the color wheel, because you have to understand that the color that we perceive with our eyes is the colors that are not absorbed by that material. So if that material is absorbing light, we should look at some sort of a model that explains that absorption and therefore the color of these compounds. For example, you worked with that green crystal, that iron oxalate coordinate covalent complex. So it was green. If we were to take that crystal and put it in one of the spec 20s, we would see that it had an absorption, I think around 520 nanometers, in that range. So it absorbs, no, I'm sorry, it would absorb, yeah, it would absorb somewhere in between these ranges and exhibit a green color over here, and that's what makes the crystal green. So it absorbs the complementary color. That's what I'm talking about. So I screwed that up. I did it completely backwards. Yeah. So that green crystal absorbs somewhere in the red, and so it looks green, just like plants. Remember, we mentioned yesterday that plants absorb in the red, and that's why a lot of plants are green. Okay. So that's the quick and dirty on light and complementary colors. Any questions on that? All righty. Now, this is kind of an interesting plate because it gives you a look of what's taking place in those spectrophotometers that you guys use in lab. So when you turn on those spec 20s or spec 200s or whatever they have in there, there's a light source in there, and that light is collimated through some sort of a prism or a grating. Now, prisms and gratings, what they do is they split light, white light, into its energies, like the rainbow. So you have that visible light that it's split into. And then you have the slit. The slit is like that knob adjustment. So you turn the knob and it turns the slit and it lets in different wavelength into your sample. So we can put in different colors of light into the sample and see what's absorbed and what's reflected. And that comes out in some sort of a readout at the end. All right, any questions on that? Okay, so we have this complex, this titanium coordinated with 6 waters, and we see that it's a +3 complex, and it says that it has a maximum absorption at 510. So it absorbs green and yellow, so it's going to look like the complement, which is, I don't know, a mixture of all the other guys. Okay, let me just move this out of the way. Okay. Now, we want to use some sort of a electronic structure theory to help us understand these color properties. So something's got to be absorbed and emitted that makes sense. And we're going to look at it in terms of these different complexes. So how can we rationalize this complex that absorbs green and yellow, and it looks like a combination of the other energies, which are mostly high energy. So it's blue, purplish. All right. The other thing that we want to rationalize using this electronic structure theory is the magnetism of these coordinate covalent complexes. So, for example, I have this complex here, cobalt with ammonia. It has no unpaired electrons, and I know that because if I put that compound in a magnetic field, it doesn't affect it. It doesn't interact with the magnetic field at all. As opposed to this cobalt compound with the fluoride, which has 4 unpaired electrons. And I can do this experiment because I can take that compound, put it in a magnetic field, and see that it deflects. And by the amount that it moves in that magnetic field, I could calculate the number of unpaired electrons. It's called a gooey balance. But anyway, we want to understand how to use the crystal field theory to explain the magnetism and the color properties that we just took a quick look at. Now, before we can even get to that, we have to rationalize this D6 cobalt 3 plus ion in both cases. So the first thing you have to see and note here, and be able to do this not only for this system but other systems, is to calculate the number of d electrons on that metal ion in the complex. But before you can do that, you have to make sure that you can see what the charge is on the metal. So you have to be able to assign oxidation states. So in this case, I have 6 ammonias right here, and we know that ammonia is not charged. So the overall charge of the complex must be solely due to the charge of cobalt. In other words, +3 plus 0 equals +3 overall. So the oxidation state of cobalt is +3. Now over here, I have this complex, cobalt F6 3 minus. The overall charge of the complex is 3 minus, and I have 6 fluorides. So that means I need 6 electrons to go to all of those fluorides. 3 of them came from somewhere else. Maybe it was 3 potassiums in this crystal. But it has 3 electrons from somewhere else. That means there must be 3 electrons given up from the cobalt. So again, cobalt is +3 in this complex and +3 in this complex. Does everybody see that? +3 in both cases? Yeah, you see that? Because you're going to have to be able to do that in order to work these problems. All right, now that's just the first step. So now we're dealing with a cobalt +3 in both cases. How does that transfer to D6? How does that mean that there's 6 electrons in the d orbitals of a cobalt 3 plus? All right. In order to do that, we need to take a look at a periodic table. So there's cobalt, right? And you know from Chem 200 and the filling order form what the electronic structure of cobalt should look like, right? So you have the 1s, the squared, the 2s squared, the 2p6, 3s, 3p6 over here with aluminum all the way to argon. And then the 4s starts to get filled next with potassium and then calcium. That would be 4s squared. And then the 3d starts to get filled, 3d 1, 2, 3, and so forth. Now, as soon as you add in an electron into the 3D, in general, for most atoms, there's a shift in the energy levels. So let's see if I can explain this a little better with a picture. Okay. All right, so when we go to fill in, there's the 4s, right? And then the 3D, 2, 3, 4, 5. 3D is higher. So I do 4s1, 4s2. As soon as I put 1 electron in this higher energy level of the 3D, this whole bunch of orbitals shifts downward and becomes a little lower than the 4s. Okay? So if I do cobalt, go back here and take a look at cobalt. Cobalt has 1, 2, 3, 4, 5, 6, 7 electrons in that electronic structure. So I got 1, 2, 3, 4, 5, 6, 7. All right. Now, since they're lower energy, when it comes time to make a cobalt 3 plus ion, I take the electrons out of the highest energy, the valence electrons out of the highest energy orbital. These guys come out first. And then one of these guys come out. So I'm left with 1, 2, 3, 4, 5, 6. So it is a D6. Cobalt 3 plus has 6 electrons in the d orbital. And that's because there's this shifting that takes place between the s and the d's. Any questions on that? All right. So let's take a look at cobalt 3+ again. Here's cobalt right here. And I'm going to have to take out 3 electrons to make cobalt 3+. I have to remember to take out the S first. So that's 1, 2 here, 3 here. And then I can start counting. So it has, at titanium, I have 1, 2, 3, 4, 5, 6. So it's a D6. And so you need to get used to calculating the number of d electrons that are in these complexes. Any questions on that? Okay. Now, once you can rationalize that, the number of electrons, then we're ready to take a look at crystal field theory. Now, crystal field theory is a way to generate orbital energy diagrams. So what is orbital energy diagrams? Remember back in Chem 200, you did orbital energy diagrams. So the energy was like this, and you had your 1s, 2s, and then the 2p, and so forth. So when you went to put in electrons into the atomic electronic structure, you always started out with the lowest energy, and then you used Hund's rules when you were putting electrons in the p orbitals and so forth. So you did it from low energy first, and then you used Hund's rules and Pauli's exclusion principles and so forth. So this is called an orbital energy diagram because it ranks the orbitals according to energy and allows you to use those rules for putting in electrons. And that's what the crystal field theory does, but we don't have to learn anything about quantum numbers. So in that sense, it's easier than the orbital energy diagrams that you developed with the quantum number n, L, m sub L, and s. Okay, so the crystal field theory, it's a way to get these orbital energy diagrams, and it's pretty visual, which is nice. So it's not that complicated, and it centers around how the coordinate covalent bond takes place. So in this picture here, I have the metal right here, and that metal, say it's that cobalt 3+, it has 6d electrons, but they're in the 3d. This empty d orbital is like the 4d. It has 4d orbitals, they're empty. So the way we envision this coordinate covalent compound happening is that, say, the ammonia molecule, say this is nitrogen here, and I got my hydrogens in all these other spots. And here's the lone pair of electrons that's centered on the nitrogen. So this lone pair of electrons comes up to an empty d orbital, deposits its electrons in that empty d orbital, and then they're shared by the metal, which is often a cation, positively charged. So there's attraction towards those electrons, and shared by that electronegative nitrogen, and that's where that coordinate covalent bond arises. Okay, but notice this is going to come together and deposits an electron and forms some sort of a stable bond at a stable distance where the repulsion of the nuclei with each other is minimized along with the repulsion of the electrons that are centered on this molecule and this one. So you find that sweet spot, and that's the bond distance, where all that repulsion is minimized and the attraction is maximized, the attraction between the nuclei and the electrons. All right. So here's an energy diagram, and it shows the energy of the whole system is way up here. Okay. When these coordinate covalent complexes form, there's a drop in the energy down to here. This is when they're formed, because now you're maximizing the attraction and trying to minimize the repulsion. But not all repulsion energies go down, right? Some of them go up. And the theory for crystal field theory is that those 5D electron orbitals are repelled. The electrons in those d orbitals are repelled with the incoming electrons from the lone pair. So there's a rise in the energy of the d orbitals, okay? But not all d orbitals rise equivalently. In this picture, 2 orbitals rise further up than 3 out of the 5 d orbitals that have electrons in it. So that causes a splitting of the d orbitals. And this is all crystal field theory. Okay, so there's a splitting, and this splitting referred to sometimes as the gap energy, or E gap, also called delta, the delta splitting, comes about through this repulsive interaction of the d orbitals, but not all d orbitals repel the same. And so 2 split from 3, and you get a gap. Now, this energy gap, this delta, is in the range of the visible. And that's the rationale for why these coordinate covalent complex have all these really nice colors, like the green crystals and the reds and so forth. So this splitting is right into the visible. And now you can imagine electronic transitions in here that can account for the colors. And also you can use Hund's rules in the filling order forms for the d electrons to rationalize the magnetic properties. How many of those electrons are paired and how many are unpaired, right? We're going to use that splitting. And that's all the crystal field theory is. This picture shows you why 2 of those d orbitals will go higher up than 3 others. Okay, so we're going to use this picture here, and what this first diagram shows is a complex that's formed into an octahedral. So crystal field theory is specific to the geometry that it's applied to. So when you talk about orbital energy ordering, or the diagram, using crystal field theory, you have to say what geometry you're applying that crystal field theory for. So this is the crystal field theory for the d electrons when there's an octahedral field of ligands. So that's what they're talking about, octahedral array, or sometimes they'll say octahedral field. So you can think of this as players on a baseball team, but here it's 6 players, be closer to a basketball team. So I have 1, 2, 3, 4, 5, 6 ligands approaching this central metal along the Cartesian coordinates of plus x here and minus x over here, plus z up here, and minus z, y, and minus y. Okay, so that's the Cartesian coordinate system, and you have the approach of the ligands along the positive and negative of each one. Now, how will those ligands and their lone pair of electrons interact with the electrons that are centered on this central D metal atom? Okay, so let's take a look at the electron density of the different orbitals, the 5 different orbitals you learned about in Chem 200. Remember, they were the dx squared minus y squared. We have the dz squared here, and then the dx squared, the dxz, the dxy. Let me shut this window. And lastly, the dyz. Okay. Up here, I have electron density for the dx squared minus y squared along the axes of the x and the y, right? So this is electron density or probability density. The electrons are going to exist in this dx squared minus y squared orbital. So you see I have the highest probability of electrons along the y and along the x. For the dz squared, I have the highest probability of electrons to be along the z axis. So these are the 2 axial d orbitals, as opposed to these 3 down here, which are the 3 equatorial orbitals, which have electron density in between the planes of the Cartesian coordinate system. For example, this dxy has electron density in the xy plane, but it's not axial. It's in between those axes. See how the lobes are in between the axes? And the same thing here. They're off-axial electron densities for the xz and off-axial for the yz. Any questions on those pictures? All right. Then I think you can see that when these ligands move in to form coordinate covalent bonds with the metal, they're moving in along the axes, and they're more likely to cause repulsion with electrons residing in the dx squared minus y squared and the dz squared, because these 2 orbitals have electron density along the axes. And these ones will repel, but not as much. So that explains the separation, that gap energy. And now we can use that to make an orbital energy diagram and put in those electrons, and then start to talk about where colors arise and how magnetic properties can change. All right, so we can go back to that titanium with water example. Titanium is a D1 metal. So it's a titanium 3+ ion. It loses 2 electrons out of the s orbital and then 1 out of the d, leaving 1. So it's a D1 metal. And the colors now can be rationalized using the orbital energy diagram that comes from crystal field theory. Okay, again, crystal field theory says the d orbitals are not the same in energy. They're not degenerate. That's another term used for same energies for all the orbitals. but that degeneracy is split. Two orbitals are higher in energy because they repel more with the incoming electrons from the lone pair of the ligand, and three don't repel as much. So they separate out, giving a gap energy. And now we can understand how that titanium complex can absorb light. When it absorbs light, it promotes the electron from the lower energy level to the higher energy. And that gap energy, like we mentioned before, that delta is indivisible. Okay. Now, why do some complexes, why are they different colors? Like why is copper with ammonia a deep blue and water with ammonia a light blue? This can be rationalized by using what's called the spectrochemical series, which is based off experiment and the ability of these ligands to split the d orbitals into different gap sizes. So in the beginning, this is the so-called weak field ligands, which don't split the d orbitals very much, so they tend to get smaller deltas. All the way to the high field splitters, where these ligands cause a lot more repulsion and make those gap energies larger. So, you know, we can use this relative size of the gap to rationalize some experiments that we see. Okay, strong and weak field splitters. Now, here's an example of a series of coordinate covalent complexes. We start out with weak field splitter fluoride and end up with strong field splitter up here, cyanide. And you can see how the gaps change, the gap sizes. Okay, any questions on that? All right. Now, you have to be able to figure out how many electrons there are in these different complexes. And we spoke about how to do that. So here's just some more practice. You know, what's vanadium? 3+ is a D-Watt system. You need to find vanadium right here. It's 23. And what was it? 3+. So how many d electrons does that have? Well, we have to remember we lose from the s first. So that's 1 electron here, 2, then 3 here. So we have 1, 2 electrons. So vanadium 3+ is a D2 system. And you have to, you know, get used to doing that too. Anyway, once we do that, we can use the octahedral field of crystal field theory to arrange those orbitals according to energy. And then we can use Hund's rules to put in the electrons. So we figure out how many electrons that system has, and then we can plug that into crystal field theory to arrange their orbital energies. Okay. So that's all nice and well. Let me try to show you what I'm talking about. So we know that crystal field theory helps us arrange those d orbitals in terms of their energies. Get that out. So I have a set of Ds that are lower than a set that are higher in energy. So up here's the dx squared minus y squared and the dz squared. Over here, those off axials, the xy, the xz, and the yz are down here. So we have all these different complexes with all different numbers of electrons in them, and you have to rationalize where those electrons are going to go using Hund's rules. All right. So if it's a 3 electrons, it's easy because I'm just going to put them in the lowest orbitals because that's going to have the lowest energy electron configuration. But now when that D goes to 4 or more, then I have a choice. That fourth electron can go here and get paired or go up here and be promoted. So which one do you think it does? This is the gap energy delta. Well, it turns out that it does what you might think if you had time and you thought about it. Nature tends to just minimize energy. So it's going to take the cheapest or the easiest way out. So there's a choice between two energies. There's a promotion of the electron, and that's going to cost delta in energy. Now, if I paired the electrons instead, oh, that's a terrible electron, but if I paired it, then it's going to cost me in repulsion. And that's called energy spin pairing. So you have to look at the relative energies here and pick whichever's lower. If the gap energy is lower, it's going to promote. If the spin pairing energy is lower, it's going to pair. Okay? And so that's how we can use the crystal field theory to get an orbital energy diagram and then rationalize why, in some cases, we would more tend to promote versus pair because the ligands are either high or low field ligands, like we mentioned back here. So there's a lot of stuff going on, but if you take your time, then you can figure out the problems that you're going to face in the homework. So you have the weak field ligands, which lead to smaller gaps and tend to promote that fourth electron and beyond. Whereas stronger field ligands give larger gaps, and in that case, the system gives up the spin pairing energy because that's smaller, and they tend to be systems that lend towards diamagnetism because there's more pairing in those systems than promoting, which leads to paramagnetism. And that's how you can get a handle on the magnetic properties of these different systems. Okay. And so back here, we have a system, cobalt with 6 fluorides. That tends to be a high spin type situation because fluoride is the weak field where you get smaller deltas. So I do 1, 2, 3, 4, 5, and then 6, I start to pair. Okay, so in this case, this cobalt 3, it's a cobalt 3 metal here, and it's a cobalt 3 metal here. In this case, I tend to promote giving more unpaired electrons, and therefore the magnetic properties of these paramagnetic electronic structures will interact with your magnetic field. Whereas in this case, delta is so big because cyanide is a strong field ligand, or a strong splitter, which leads to large deltas. So it's cheaper to do 1, 2, 3, and then the fourth electron pair it, because you have to spend the ESP, the spin pairing energy, which is going to be smaller than the gap energy for these cases. All right, so any questions on that? Okay, now just to finish off the rest of the chapter, you won't be using these as much as the octahedral field, and that's the tetrahedral and the square planar. So we have those different possibilities of ligands coming in a tetrahedral field. For the tetrahedral field, the ligands, there's 4 of them, and they're envisioned to come in off axial versus the axial, and therefore the complexion of the orbital split is opposite. So you have the axial d orbitals repelling least in the tetrahedral field, so they're lower energy than the off axial orbitals in the d, where the ligands are coming in a tetrahedral field. Also down here it says, I think most tetrahedral are high spin because deltas tend to be small for those complexes. And then the last is the square planar. You can think of the square planar as the octahedral field with the Z ligands popped off. So consequently, any orbitals with Z nature in it go down in energy because there's no repulsion. And anything with the X and Y nature tends to go up in energy. So it looks just like an octahedral field where the axials are above the off-axial orbitals, except anything with Z nature, like the dz squared, goes down in energy. Anything with X and Y goes up in energy, here because of the Z here, it goes down a little bit in the square planar. So the square planar looks a little more complicated, but like I said, most of your problems will deal with the octahedral field, not so much. I'm not sure if there's any really with the square planar or the tetrahedral. And so that's it. Any questions on the material for this chapter? All right, I'm gonna